either come up with a formula, we can find a value for omega. The amplitude is 5 meters, and we can do the exact same process we did before where we pull it out, let go, and the thing oscillates back and forth, or, we don't have to imagine it horizontal, we can do it the same thing here. We can ignore the gravitational potential energy as long as this is our equilibrium. If we choose this as our equilibrium, we're bringing mg back into it. All right, questions up to here? I assume someone would have shouted out a question. All right, so while we're on the topic of simple harmonic motion, is there anything else that is kind of like simple harmonic motion, but it's not quite? Well, the answer is yes, because otherwise it would be a really bizarre question to throw in right now. So we're talking about the simple pendulum. Supposedly Galileo did a lot of work in this area, but explicitly in church, he was looking at the chandelier that was swinging back and forth and was thinking physics. As people are wont to do in church sometimes, and think about physics. So this is I'm going to start out at some initial angle theta. I got some mass here. Now a couple characteristics of simple pendulum. One, frictionless. We are also assuming that the string right here, or whatever is holding this mass a certain distance away, that this is massless. Or we can word it slightly differently, all the mass is in a point mass on the end. We're going to throw in one other criteria, but we need to get there first. Of why, basically you're going to get to a point where we need to justify it. Questions on at least what I'm looking at here, what a pendulum is. Let's start where we often do. Force diagram. What are the forces acting on the mass?
Weight. Yeah.
Weight.
Tension from the
And tension. That's some angle theta right there. Again, I mentioned a vertical right here. These are parallel to each other. Two parallel lines cut by a transverse. Alternate interior angles are congruent. In other words, that angle there is theta. Which way is this thing going to start moving when I let go? I got you. That way?
Yep.
We have dealt with different pendulums in our days then.
When you let go, you pulled it back to there. And
I pull it back to there. And what you're saying, let's see, that's about even with my elbow. That thing's going to go right for my elbow.
It's gonna go down at an angle.
Yeah, it goes down. And the difference there is important. It does not travel this way, which is what I saw two of your fingers pointing in that direction. It's not going to travel that way. It's going to travel down. So it's going to travel in that direction, perpendicular to the tension. So at this moment in time, its acceleration will be in that direction. It starts at rest, and then when I let go, it has to move in the direction of acceleration. So it's starting to rest. So my acceleration is in that direction. So we set up a coordinate system like we've done so many times before. Do an I hat, J hat. I do want to point out that we have dealt with problems where linear motion problems, the object's going to, basically there's just a change in speed. We've dealt with problems with centripetal motion where there's a change in direction. Now we have change in speed and change in direction, both involved here. Although part of that we were not going to care about, but they are both existing here. So I need to break weight up. Tension's already my J hat direction, so I need weight is not in I or J, it's in a combination, so we need to figure out what that combination is. So I need to figure out how much is in the direction of acceleration and how much is perpendicular to it. So I got my right triangle set up here for breaking this up. And so either this one is theta or that one is theta. Which one's theta? Let's draw it bigger, just to suppose this tension is in this direction and weight is down. That angle there is theta. So breaking up into, so you got something perpendicular. So I got my, that's a right angle there. Let's see if I can draw that a little bit more rightish. That's my right angle there, and I got my two angles. I got an angle here, we'll call it angle 1 and angle 2. One of those is equal to theta. Based on the way I drew it the second time, which one of those angles seems more like theta? Yes, it is. What was your thought process?
I was just looking at just visually the angle of 2.
Yeah. That's a fat angle, that's the fat angle, that in essence. From a geometry point of view, that's a right angle right there. I know that this plus this have to add up to 180 degrees. So since 90 is taken out of that, this and this must add up to 90 degrees. So this has to be the complement of theta, which I generally label something like theta prime. And so that has to be theta down there. So if you get stuck, try to draw it. I naturally just draw almost everything at a 45-degree angle, whether it is or not. So it's hard to tell. Make it more extreme. All right, so I've got my angle down here is theta, which means my opposite side is the weight times the sine of theta, and this one must be W times the cosine of theta. So in essence, what I'm left with is tension acting up at an angle of theta. Opposite direction is W cosine theta, and perpendicular to that, W sine theta. So we did fourth diagram, direction of acceleration, coordinate axis, decomposition, equations of motion. What are my two equations of motion?
For J hat, it's going to be Ft minus weight cosine theta equals 0.
Not equal to 0. Why is it not 0?
All right, I want someone going down. Because, wait. I don't know.
Yeah, if we had done axes like this, then it still wouldn't be equal to 0. Why is acceleration not equal to 0 for the tension and W cosine theta? I had hinted at it in my prologue to this problem. All right, we'll come back to it. What's the other equation?
Weight sine theta equals an A.
In the other case, the first equation, second one, yeah, I'm fine with that. In the first equation, describe the path that this bob is gonna take, that this mass is gonna take. Is it down? All right, what you're saying and what your hand gesture are not the same.
Down, but at an angle.
So it's gonna be like a line drive?
Kind of like a weird swooping motion.
Curve.
Okay. It's a curve. So we have centripetal acceleration involved here. This would be centripetal acceleration, or mv squared over r, or m omega squared r. The fact that it is changing direction makes this one not equal to 0. Now, we're not gonna have to deal with it. This is just sort of throwing it in, sort of connecting some of the other stuff that we've done. It's the second equation that actually becomes more critical for the simple pendulum. Now, I do have to throw in one other thing here. And I think every time I do this derivation, every time I do this bit, I make the exact same mistake. And one of these days I'm gonna, well, actually, it's only gonna get worse from here on. So, but I still keep making the same mistake. So there's a tradition that I'm maintaining. But at least I'm filming it now. At this point right here, we established our positive direction was that way. Except I've had this thing pulled back in the opposite direction. This thing is pulled back this way, but the other way is positive. And so technically, this is negative theta. So cosine and sine of negative theta. I'm going to rewrite, throw the extra negative sign there, so W sine of negative theta. Negative there. So the question is, what's the sine of negative theta? And what's the cosine of negative theta? Well, pull out your calculator, if you got it. Do the cosine of 30 degrees, or if you're in radians, 30 radians, doesn't really matter what angle you pick. And then the cosine of negative 30, radians or degrees, whichever one you like. And then do sine of 30 and the sine of negative 30. Jacob, did you want to borrow a calculator?
Yeah, I'll borrow one. Thank you.
Yep.
It's just the opposite. It's
Which
the
one?
opposite sign of, so the positive would be negative,
Sine of 30 is 0.5. Sine of negative 30 is negative 0.5.
Yeah, you were getting something different?
I'm probably in a different mode. so-
Yeah. But the same thing should
Yeah.
show up where you got negative on the other one.
Yeah.
Yeah. So if this was degrees here, then this would be 0.5 and negative 0.5. If it were radians, since I think that's what you had,
0.988.
0.988 and negative, well, the first one was negative,
So, yes.
and then positive 0.988. There was one test where I actually set it up so that all the angles that I used was the same value if you were doing radians or degrees, just to eliminate that. And then I asked a bonus question of why did I pick those angles?
You can
I
do
think
it
there was
again.
one person who actually saw it, but, sorry, Brandon.
You can do it again if you like.
You know, it's just about how much preparation I put into that aspect of it. Cause I have to find my document, or I either rederive it, or I have to find the document where I wrote them all down. Cosine of 30 and cosine of negative 30?
Cosine of negative 30 is 0.866. That was the other one, negative 30. Cosine of negative 30 was 0.866.
And positive 30?
Negative. Wait a minute, let me do it again. Didn't look that.
I got positive for both.
Yeah. And you, if you're radians, it would have been something really small.
Yeah.
0.154.
0.154? You're dealing with radians. All right. If we actually look at, if you think about trig functions, for those who haven't had trig yet, here's a little, yet another sneak preview. If this is a circle, about to say, at least this one is filmed, but no, they just saw me throw it off to the side. So if this is a circle of radius equal to 1, then if whatever this angle is right here, it's gonna cross the circle, this point where this line and the circle meet is gonna be the cosine of theta, sine of theta. If the angle's negative, you're going in the other direction. So this would be negative theta. And it really helps for this example if I drew it a little bit better. So the x value, in an ordered pair, the x value is the same. The y value, on the other hand, is the negative. In more slightly different wording of the exact same thing, cosine is an even function. Sine is an odd function. Odd functions, f of x is odd if, let's see, odd function is equal to the negative f of negative x. An even function, f of x equals f of negative x. Just some bonus knowledge. So the cosine of negative theta here is just going to be cosine of theta. So what we had written down there was correct the first time. So this just becomes ft minus w cosine of theta is equal to m, doesn't matter which one I take, v squared over r. The second one though, this negative sign comes out front. So we have negative w sine theta is equal to ma. That's the one that we will explore. Now, if you recall, back to when we started doing simple harmonic motion. Simple harmonic motion will work if the force, negative k delta x, is equal to ma. If my displacement and my acceleration are opposite each other. And from what we did in chapter 2, acceleration depends upon the displacement. Remember that acceleration is the change in velocity over change in time, and velocity is the change in position over the change in time. Acceleration and position are very much related to each other. And so I would really be cool if we can get this in that format. However, I've got acceleration and sine of theta. So we need to somehow get it more in that form. Because, yeah, there's a relationship between theta and a, but sine of theta and a? So first off, a is linear, theta is angular. Let's get a common language there. Let's make this length L. know V equals omega R, A equals alpha R, S equals theta R. Now this is the one that you're probably more familiar with, but this is the one that we care about right now. A is alpha R, so I'm gonna take my equation there. Negative W sine of theta is equal to mass times alpha times L. So this is negative mg sine theta is equal to ml alpha. My m's cancel out, so I'm left with negative g sine theta is equal to L times alpha. Now, at least we've eliminated some stuff here, but we still have this issue of alpha and theta. At least they're probably in one sentence. At least they are now both angular variables. But we still have this trig function to deal with. And this is why we started out the bit by saying, is there something that is close to simple harmonic motion that we can pretend in some cases, whatever the wording is. Have we done small angle approximation in here? We did, okay. And what is small angle approximation?
Small enough to be considered zero.
No, not that small. Well, yeah, okay. It would work if theta is equal to 0, but we don't want to make that assumption. That'd be very boring problems. I have a pendulum that's hanging straight down. What's the period? Either 0 or infinite, I'm not quite sure which. Frequency is 0 because or infinite.